A linear polymer is a polymer molecule in which the atoms are connected end to end along the whole length of the chain. This chain is called the backbone. The long chains are typically held together by the weaker van der Waals or hydrogen bonding. Since these bonding types are relatively easy to break with heat, linear polymers are typically thermoplastic. Heat breaks the bonds between the long chains, allowing the chains to flow flexibly. For some example, like polyethylene, PVC, and polypropylene. Normally, some of these atoms in the chain will have small chains of atoms attached to them. These small chains are called Pendle groups. The chains of Pendle groups are much smaller than the backbone chain.
Next, I will going to explain the branched polymer. Branched polymer is a polymer chain having branch points that connect three or more chain segments. It can be short branches or long branches. These branches are known as side chains and can also be very long groups of repeating structures. One of the examples of branched polymer is polypropylene shown in the figure. It consists of main chain, side chain, or we call as branches, as well as repeating structure units which are called monomers. These branches in a polymer decrease the ability of cross-packing of the chains, thereby reducing the degree of crystallinity of the polymer. As we know, the higher the density of the polymer, the higher the degree of crystallinity and the harder and stronger the polymer. Since these branch chain polymers are regularly packed and therefore they have low tensile strength, low density, boiling point, and melting point than linear polymers. Therefore, the number, size, and type of side chains has a significant effect on the thermophysical and mechanical properties of a polymer.
The cross-linked polymer look like ladders. The chain links from one backbone to another. So unlike linear polymer which are held together by weaker van der Waals forces, cross-linked polymer are tied together via covalent bondings. This much stronger bond make most cross-linked polymer thermostatic. With only a few exceptions to the rules, cross-linked polymer that happen to break their cross-link at relatively low temperature. If we are able to introduce cross-linking bond between adjacent molecular chains, this adds form stability at higher temperature. But there will still be some losses of strength at elevated temperature, but the cross-linked molecular chains are much more resistant to flow when stress is applied. In general, mechanical characteristics are improved, especially at higher temperature. It results in improved resistance to stress cracking and better fluid resistance.
Now, I would like to explain what is network polymer. It's almost similar with the cross-linked polymer, and hence we can say it is the evolution of cross-linked polymer. Network polymer is a highly cross-linked polymer that includes numerous interconnections between chains. Its monomers link together to form 3D network structure. For example, bakelite is a thermostatic polymer that contains polymer chains with cross-link. Diagram 1 shows the network structure of network polymer, whereas diagram 2 shows the molecular structure of bakelite. As you can see from this slide, network structure have the greatest strength among other type of molecular structure. This is because the monomers of network structure have strong covalent bonds. Due to the strong covalent bonds, it has the stronger intermolecular forces that hold atoms together within the molecule. Hence, it has the properties of hard and brittle.